Okay. All right. This is section 3.4. And here we're going to deal with complex numbers. And what we're looking at is getting into complex roots. And if you remember the last few sections, we talked about real roots. Here we're going to talk about complex roots. But before we do that, let's sort of fit this all into a big number. Complex numbers are sort of the overarching thing, and they're in the form of a plus bi. I is the square root of -1. So when you come out of here, sub below that, we've got real numbers. These are what you've been dealing with. Real numbers, b is 0. Okay? We also have imaginary numbers. By the way, this nomenclature lies. Imaginary numbers are no more imaginary than real numbers are real. Imaginary numbers, a is 0. In other words, all you've got is just this term here. Okay? And the reason we've got this is based on our numbering system. We used to be dealing with positive square roots. Unfortunately, a lot of applications, especially electrical engineering, you get a lot of negative square roots, and they are important. Okay, below the real numbers, we've got things like rational. These are things that can be expressed as fractions, and irrational. You listed these are things that can't be expressed as fractions. Pi is an old friend. Square root of 2 you saw last year. Square root of 3 you saw last year. E you saw last year. These are all irrational numbers. Subset of rational numbers are integers, which is -1, -4, no decimals. And then below there we've got our whole numbers or counting numbers. And these are 1, 2, 3, on and on and on. This is how all of this fits in to this great big picture. So let's deal with imaginary or complex numbers, which by the way are not. 3 minus 6i. 3 is the real component. And the -6, not the I, just the -6 is the imaginary. And we're going to deal with these just like we deal with binomials when we do arithmetic on these things. Okay, so -6 is the imaginary, not -6i. Okay, complex arithmetic, which again is not. I've got 2 plus I plus 3 minus 2i. So this is the same thing. You add your real terms, 2 plus 3, and then we add the imaginary. So I've got 1 from here minus 2 times I. Now I simplify. 5, 1 minus 2 is a -1i. And that's the result from that one. Now let's deal with something a little bit harder. Minus. Okay, all this is you're distributing this -n. So it's the same as 2 plus I plus -3 plus 2i. Just bring the negative in. And here again, you put together your like terms. I'll have 2 minus 3. Those are my reals. Plus my imaginaries. I have a 1 plus 2i. That gives me negative 1 plus I. And that's how you add and subtract. Multiplication is just like you do with binomials. 2 plus I, 3 minus 2I. So you distribute this 2 in. So that's going to give me 6 minus 4I. And then I distribute this I. That gives me plus 3I minus 2I squared. Okay, I'm going to pause here a little bit and let's talk about this. I is the square root of negative 1. So I squared then would be the square root of negative 1 squared, which is negative 1. I cubed then would be I squared times I. We know I squared is negative 1, so that would be a negative I. And I to the fourth would be I squared squared, which would be 1. The one we're interested in is this one right here. I squared is a negative 1. So whenever you see an I squared, you substitute in a negative 1. So I'm going to have 6. I'm going to go ahead and combine these I terms, gives me minus I. And then I squared is a negative 1. So I'm going to have minus 2 times a negative 1. That's going to give me 6 minus I, negative and negative, plus 2. And then I combine these. That will give me 8 minus I. And that's how you multiply. Do not ever leave it as I squared. Remember to substitute in a minus I. Okay, let's deal with one that's a little bit harder. As usual, division. Now, like fractions, you never divide by another complex number. We're going to introduce terminology here called a complex conjugate. Which means you change the sign of the imaginary term. And in order to divide by these, what you do is you do the complex conjugate of your denominator. So the complex conjugate of 3 minus 2i, all right, so its complex conjugate will be 3 plus 2i. You change the sign. So I'm going to have 2 plus I. I'm going to multiply top and bottom by the complex conjugate of my denominator. And you'll see why here in a bit. And then I do my distributing trick. So I end up with 6 plus 4i. And you should recognize this as something we've already done before. Plus 3i plus 2i squared. Remember I warned you about this. That's a negative. So this term becomes a negative 2. So I'm going to have 6 minus 2 plus 4 plus 3 times I. 6 minus 2 is 4 plus 7i. And that's my numerator. Okay? That's only my numerator. So now we need to come back in and do the denominator on this thing. Okay, well it's this one. So I'm going to have 3. I'm going to distribute just like before. 3 times 3, that gives me 9 plus 6i minus 6i. At this point you should see what's going to happen. Minus 4i squared, which makes this a plus 4. Substituting the negative 1 there. Plus 6i minus 6i becomes 0. That now becomes 9 plus 4, which is 13. So now I put them together. I have a 4 plus 7i over 13. Now to simplify this, you have to see if you can simplify both of these terms. In this case, you cannot. 4 will not go into 13, nor will 7. And so this becomes your answer right here. Now remember, to find the complex conjugate, you change the sign only of the imaginary part. All right, so now that we've learned all of that, how does all this fit into roots of polynomials? And the reason is complex roots occur as conjugate pairs. In other words, they will occur as a plus and minus bi. So if you found a plus bi, a minus bi will also be a root. And let's take a look at an example of a complex root. So let's deal with x squared plus 9 equals 0. You want to find the zeros of this. Okay, typically you would think quadratic, but I don't have an x term. So I could just move my 9 over, and then we take the square roots. And so I end up with x equals 2 the square root of negative 9, which equals 2 the square root of 9 times the square root of negative 1. So x is going to equal to square root of 9. It's going to be plus and minus. You have to do both of them. Remember, it's a conjugate pair of 3. And you should recognize this as being I. So there are my two complex roots. Notice these are purely imaginary. I have no real component to this at all. Now let's deal with how this shows up and something a little different, like x squared minus 4x plus 5, and you want to find the zeros, which equals 0. Okay, so the first thing we're tempted to do is go in and factor. I want 5 and 1, all right? That will add up to a negative 4. And these are, because this is plus, they're either going to have to both be positive or both be negative. And there's no way, the only factors of 5 are 1 and 5. There's no way to take a positive 1, a positive 5, or a negative 1 and a negative 5 and get this. This cannot be factored. So you have to put this into the quadratic formula. A is 1, B is negative 4, C is 5. Okay, so negative b plus or minus the square root of b squared minus 4ac all over 2a. This ought to look pretty familiar by now. And we plug in. We're going to have a 4 plus and minus the square root of negative 4 squared is 16 minus 4 times 1 times 5 all over 2 times 1, which is 2. Okay, so now we're going to come in and you're going to have 4 plus and minus the square root of 16 minus 20 over 2. I'm going to have 4 plus and minus the square root of a negative 4 over 2, or 4 plus and minus the square root of 4 times the square root of a negative 1 over 2. I'm going to have 4 plus and minus 2I over 2. You can simplify this. You have to do 4 divided by 2, but you also have to do this because of the plus and minus. So 4 divided by 2 gives me 2, and 2 divided by 2, the I. And there is our conjugate pair. I've got 2 plus I and 2 minus I. And those will be our two roots.